Welcome to this next video based on the series called Magic with Similarity, and we hope that you quickly realize that similarity is a very strong tool, and therefore you will try to do some problem solving with similarity. So this particular lesson is on Ptolemy's theorem, which is a very pretty result to do with cyclic quadrilaterals. So you take any quadrilateral which is cyclic, and let's label the vertices of the cyclic quadrilateral as A, B, C, D, and the sides as A, B, C, and D. Now, any cyclic quadrilateral will have two diagonals, and we'll label them as well D1, D2. So Ptolemy's theorem says that D1, D2, which is the product of the diagonals, will be equal to the sum of the product of the opposite sides. That is, if A and the opposite side is C is added to B, whose opposite side is D, and AC plus BD will be equal to D1, D2. You can clearly see that Ptolemy's theorem is very pretty, and it applies to any cyclic quadrilateral. Now, there are many proofs of Ptolemy's theorem. The one that I'm talking about is based on similarity, and it is taken from an article that appeared in Quantum magazine, and which was in collaboration with the Russian magazine Quant. And the big difference, of course, that Quantum magazine is in English, and it'll be possible for me to also attach the original article in my Google Classroom. So let's quickly point out how the proof goes based on similarity. I think I'll be able to present the essence of the proof, which is to spot two pairs of similar triangles. So here, to show you perhaps both the pairs of similar triangles on the same board, I attempt to do it twice. So here I have the same cyclic quadrilateral. So I'm attempting to draw in such a way that it's the same figure drawn twice, and we have our cyclic quadrilateral ABCD, and I need to show you two pairs of similar triangles. Now, once you spot the two pairs, it is fairly easy to complete the proof. But the two pairs do depend on one clever construction which is not obvious. So we'll have to just take the construction from the author's article. So the construction depends on finding a point M in a very specific way. This point M is located on the diagonal D2. So let's also label them. This is D1 and the other diagonal is D2, and this is D1 and the other diagonal is D2. Okay, so how do you spot M? So I shall show that presently. You have to draw a construction line MC in a very specific way, and that specific way is that these two angles that I'm now going to presently mark with green have to be equal. So this angle that I'm marking now with green will be specifically constructed such that it is equal to this angle that I have shown in the picture. So once again, this angle that I have shown in the picture, or marking in this picture, will have to be equal to this angle. So once you make this construction, then I can show you two pairs of similar triangles on this construction, and then it's very repetitive proof. So let me show you the first pair of similar triangles. It's very easy for me to show you the first pair of similar triangles, and this is the one triangle and this is the other triangle. Now, these two triangles are similar. If you think about it for a few seconds, it will be pretty obvious to you. One pair of angles is already equal, that is a green angle. Green angles are equal because of construction. And now I'll show you another pair of angles which are equal with the red. So I'm marking it with red. So this angle and this angle that I'm marking it with red are similar. Now this reason is very easy for you. You have done so many problems now on the inscribed angles. So these are inscribed angles, a pair of inscribed angles. They are equal, and with that the two white triangles on the left are similar. So let us write it down neatly. What we are saying is, let's get the angles right. The first white triangle ADC, okay, is similar to, now angle A is equal to angle B, and angle C is also equal to angle C, and that leaves M here, right? So once again I repeat, look at triangle ADC, which is the first white triangle. Look at triangle BMC, which is the other white triangle. Now it's pretty obvious that A is equal to B. A is equal to B. Let me draw this again. Okay, so A is equal to B, that is the inscribed angles, and C of ADC is equal to C of BMC, that is because by construction, and therefore these two triangles are similar by AA, right? So what is the implication? The implication is that AD over BM is equal to DC over MC is equal to AC over BC. Okay, so this translates to AD, which is okay, I haven't labeled the sides now. Let me label it now. A, B, C, D. Okay, so here we go again. A, B, C, D. All right. So what is AD? AD, please look into the picture. D over BM. Okay. So I shall write BM is equal to DC, which is C, divided by MC, which actually I'm not interested in really. I'm not interested in MC, so let me just tell you clearly that I'm not interested in this part, but I'm definitely interested in the last part, which is AC. Please look into the picture now. AC is D1 and BC is B. Now cross multiply the two ratios that I'm interested in, and I've got BD is equal to D1 into BM, and this is half of the proof. Now please look into the second picture, and you need to locate another pair of similar triangles. Now I shall simply write it down here. Triangle DMC will be similar to, so DMC. So let me just draw the outline of this triangle with white. I've already said DMC. Okay, I've drawn it with white. DMC is going to be similar to, I'm going to mark the other triangle now with white, which is this triangle. Just going to mark it. It's hopefully it will not be very confusing. This is triangle ABC. Now let's see. Angle D is equal to angle A in ABC. So angle D is equal to angle A, and what is not obvious is that angle C in both the triangles is same, and that would leave M, that will leave B here. So these two triangles are similar. So our claim is that angle A is equal to angle D. Now that is pretty obvious due to inscribed angles. What is not so obvious is that the angle C in both the triangles that I've talked about are same, but this will just take you a few minutes of thought. But once you get this similarity, or maybe I should leave this last part as an exercise now that I've clearly told you which are the two triangles I'm referring to. So then dm over AB will be equal to MC over BC will be equal to DC over AC. So let me just translate that. I'll make some space for myself. Let me just translate that. Please look into the figure now. dm is something that I really need. dm, our AB is A, is equal to MC is something that I'm really not interested in. So once again I shall tell you that I'm not interested in MC, and now I shall continue with DC. Well, DC is C, and AC is D1. Okay, so there we go again. We have, please do the cross multiplication. AC will be equal to D1 into dm. So this is the symmetric counterpart result due to the other two similar triangles, and this was the first pair of similar triangles, this was the second pair of similar triangles, and all I need to do now is add them. BD plus AC equal to D1 into dm plus bm, and please look at the figure. dm plus bm is actually equal to d1 into d2. That's the end of the proof. I think I made a hash of this one, but I do hope that you will just go through the few steps that are required, and that completes the proof of Ptolemy's theorem. But the most important thing I really wanted to convey was that once again it's our favorite new idea that we've learned in geometry, and that is similarity. So similarity plus inscribed triangles have once again come up with the magical result, and that is really what I want you to remember. As you do more and more problems in inscribed angles and similarity, you will realize that you will be able to tackle fairly interesting problems with these two ideas. And there's a third idea that I want to develop in the next few lessons, which is called the method of areas. But till then, goodbye.